Hello, welcome back to 10-Minute Science, where we take a topic, tear it apart, dissect it, and learn about something amazing in 10 minutes or less. Remember, that's plus or minus 12 or 13 additional minutes. Today we're going to talk about the tides on the Earth. And the tides, as you know, are the phenomena when the water level in the oceans and the coastal regions comes in and kind of rises and goes inland. We call that the tide coming in. And then after a period of time, it begins to recede and go out, and so the water level goes down. And then later on, a period of time later, it comes in again, and then it goes out again. So we want to talk about how this happens. It turns out that tides are more complex than you might initially think. There's the simple explanation, which you could do in about 10 seconds, and we can just say the moon causes the tides. But we want to go deeper than that and try to learn something and understand a little bit more about how it happens. And also we want to talk about the concept that the tides don't seem to affect, very much anyway, rivers, lakes, and streams. I mean, they do actually technically affect it a little bit, but not as much and not as pronounced as the oceans, the coastal regions of the planet. So we want to talk about that. There's a lot to unpack here, and there's a lot of misconceptions out there with other explanations. We're going to try to dispel those as well. So we know that the tides are a result of the moon. So that was known for a long, long time. So we need to start there. We need to draw a picture of the Earth-Moon system. All right, so here is these are just going to be cartoons, and they're definitely not to scale. So here we have a small body we call the moon, and here we have a larger body right here, and we're going to call that the Earth. Now, it's not to scale at all, right? The distance, the sizes, none of the stuff is to scale, but that's okay. We don't care about it being exactly the scale. Now, what we're going to do is define the center of the Earth to be right here, and we're going to call it some distance r from the center of the moon. Why am I defining the distance between them? Because the equation that governs gravitation is called Newton's law of gravitation. Now I'm going to write it down on the board, and we're not going to calculate with it, but I want to write it down because it's important for the phenomena of the tides and how it all works, right? But just know that we know that Newtonian gravity, as I'm going to write it down, is not really correct. It's pretty darn close, though. Newtonian gravity equations are good enough to get astronauts to the moon, calculate the trajectory of spacecraft to the moon and things like this, but Einstein's equations of relativity are actually much more accurate. We're not going there. We don't need it for this discussion. We're just going to stick with Newtonian gravity. All right, so what is the equation of Newton's law of gravitation? That means is the force, the gravitational force between any two bodies in the universe is some gravitational constant g, which is just a number, so don't get too worried about it, it's just a number, times the mass of the two bodies. So in this case, since we have the Earth and the moon, it's going to be the mass of the Earth times the mass of the moon. So this is the mass of the Earth, the mass of the moon, but then it's divided by the distance between them, but not just the distance between them, the distance between them squared. So this is what we call an inverse square law. Now, interestingly, gravitation has this inverse square law, and also electric forces, positive like charges repel and opposite charges attract. The force of electrical forces are also an inverse square law. It looks very similar to gravity, okay? What this means is that as you make the two bodies bigger, the mass of the Earth, if you make it bigger, then the force of gravity between the two bodies go bigger. This force will be the force that the moon pulls on the Earth and the force that the Earth pulls on the moon. That's what this force is calculating. If you make the mass of the Earth bigger, then the force goes up. If you make the mass of the moon bigger, then the force between them go up as well. If you make the distance between them bigger, then you're dividing by a bigger number, and then the force goes down. However, you're not dividing by r, you're dividing by r squared. And what that means is if you, for instance, make the distance between them two times bigger, if you take the Earth and the moon and make the distance between them 2 times larger, then the distance here would be, instead of, it would be dividing by, you would put in a 2r there. And since you're squaring it, if you make it 2 times bigger, 2 squared is 4, so the gravitational force would go down 4 times. So because r is squared, if you double the distance between the objects, then because you're squaring a double, then you're really dividing by 4. So punchline, if you make something, two bodies twice as far away, the gravitational force is not twice as weak, it's actually 4 times weaker. This is the same way electric forces work. If you make them twice as far away, then the force between them, if they're attractive, is 4 times weaker, and so on, because it's an inverse square law. All right, so these things are attracting each other, and we know that the moon is orbiting the Earth. We're going to talk all about that, and we know that the Earth is rotating and the moon is also rotating. And then this whole system is actually going around the sun. And the sun and the whole solar system is going around the galactic center, so everything's in motion. But in order to talk about the tides, we have to eliminate all of those other influences. It turns out that the sun does affect the tides on the Earth also. But we're going to ignore that for now because it's just additional complication. We're only going to talk about tides due to the moon's influence, and we're going to assume in the beginning that nothing is rotating here. Earth is not rotating, moon is not rotating, moon is not orbiting, none of that. We just have two bodies in space like this. In other words, if I could go outside the solar system and snap a picture, I might see the Earth and the moon like this, something like this. Now, what happens to the water on the Earth? If nothing is moving, no rotation of the Earth, no rotation of the moon, no orbiting of the moon, everything is motionless and stationary. Of course, they're going to be attracted to each other, but if you just freeze time and look at what's going on, what you would see is that the oceans on the Earth, let's pretend there's actually no continents, and there's a crust, but it's the entire surface of the Earth is covered with an ocean that covers the whole planet. Just pretend that for a second, okay? Then what you would see if you could go outside the solar system is the ocean would sort of bulge in the direction of the moon like this. Now this is something most people can understand because they would think, well, the moon is attracting the water, right, or something like this, and pulling it this way. However, the weird thing is, on the side opposite of the moon, the water is also bulging out like this. Now this part, and I don't have it drawn to scale, I apologize for that. They should be pretty close to the same, So we'll do something like that. So they're supposed to be the same in this drawing. This part, the fact that the ocean bulges on the other side of the Earth, that bakes most people's noodle at first. And what I mean by that is it's very confusing. It's non-intuitive. You would think that since everything is being attracted to the moon, that of course this side should be pulled toward the moon, but this water should be pulled toward the moon and it should be flattened over here. But it's not like that. We know it's not like that. So we have to, in this lesson, understand the tides, but what we're going to do also is try to understand why the bulging of the oceans happens the way it does. Why do we have two bulges along the Earth-Moon line like that? Why do we have two bulges instead of one? So stick with me till the end of the lesson. We're going to answer that question, but I need to move past it just so we can kind of understand the tides first. So for now, just accept as fact, because it is fact, there's no disputing this, that the ocean does bulge slightly in the direction of the moon, and also on the other side of the Earth, opposite of the moon, it bulges in a similar manner. And by the way, when the tides come in and the tide goes out, the difference between high tide and low tide along a coastal area is about 1 meter, 1.5 meter there. And also, we're going to get into this also, not only does the ocean bulge and the tide goes up, but actually the crust of the Earth, the actual physical ground we stand on, has a similar effect. But because the crust is more rigid, the high tide of the crust is only about 30 centimeters. So believe it or not, throughout the day, the ground beneath you is lifting you up about 30 centimeters when we get kind of lined up with the moon. And then when we go to low tide, the Earth's crust relaxes and so on. We can measure this very accurately with GPS. We know it's real, all right? But we don't notice it because it's so gradual, right? Of course. All right, so what we want to do is try to figure out why we have the two bulges. That's the great mystery. I need to save that for the end. For now, just accept that this is the situation. How does it lead to tides? So here we've drawn it as the bulges are essentially the bulges are kind of in a straight line with the moon because the moon is here and it's attracting it and all that stuff, right? But actually, now I need to introduce a little bit of rotation. So what I'm going to do is draw the same system over on the other board. Actually, maybe I want to do it down below here. I want to draw the same system over here. So what I'm going to do is I'm going to draw the Earth like this. And of course, I didn't draw it the same size. Apologize for that. But here's the Earth, and over here is the moon. So same exact situation. The only difference is now we're going to draw how everything is rotating, right? So what's going on is the Earth is, I'm looking down at the North Pole of the Earth, okay? The Earth is actually rotating, so this is like the North Pole. You can put like North Pole if you want to right there. It's rotating like this. All right, we know it rotates 24 hours in a day. And the moon is actually also rotating in that direction. A lot of people actually aren't aware that the moon rotates on its axis, but of course it does. We see the same face of the moon because the moon is orbiting the planet. The moon is going around the Earth, orbits. It orbits the Earth like this, but it's rotating. So what's going on here with the Earth and the moon is moving around, but it's rotating at the perfect rate, so that as it goes around, you see how my thumb is right here? Let's focus on my thumb, right? Here's my thumb. And if I did not rotate this ball, then as I go around, I would see a different side of the moon over here. My thumb is over here. My thumb is over here. I would see different pieces of the moon. But as I rotate my hand, as I go around the Earth, the thumb always faces the Earth. And as you know, we always see one side of the moon all the time. We never see the dark side of the moon or the other side of the moon. It's really not dark, by the way, but we don't see the other side of the moon from Earth. I'll have another lesson entirely devoted to why that happens, because it's really interesting. But for now, just know that the moon is rotating and it's orbiting around the Earth as well. So now that we introduce this rotation, which we know is happening, the bulging of the oceans doesn't really happen along a direct path to the moon. Actually, I'm exaggerating it here, okay? But it actually bulges more at an angle here, and I'll try to draw my best. Here's the two bulges. You see how I've cocked it at an angle like this? So what I'll do is I'll kind of like draw a little dotted line through here, just so that you can see the kind of the angle here. So there's some angle here. Call it angle theta if you want to. So the bulging is actually not lined up exactly in the direction of the moon, but it is caused by the moon. Now, why is the bulging acting at an angle like that, or kind of tilted like this? Well, it's because you have this enormous body covered in water, and the water is bulging, but then it's spinning. So imagine you have a coffee cup, right? And you put syrup inside, or just water if you want to think of it that way. Now, if you rotate the cup very slowly, then the sides of the cup, the water or the liquid or the syrup is not really going to be affected too much by it, right? But if you try to rotate this thing so that the fluid cannot get out of the way and it's kind of stuck to the side of the cup, the friction there is going to drag the syrup with the cup. So you're going to see kind of a swirly pattern in there, right? If you rotate the cup, because the side of the cup is kind of touching the water, the friction there is going to drag the fluid with it, and it's going to be dragged in the direction of rotation. What's going on here is we have this enormous liquid around the planet that's bulging, and a huge rotating object, and it's dragging this bulge and dragging it in the direction of rotation. So the moon is causing the gravitational bulging of everything, but because the Earth is rotating, it's actually slightly cocked, and it's a little bit ahead of where the moon is. And that's important for other topics I'm going to talk about in another video. Now, all we've established so far is that we have an Earth and we have a moon. Earth is covered in water. We're idealizing it there. The moon is orbiting, and the moon, because of some gravitational interaction that we have to talk about in more detail, is bulging the oceans towards the direction of the moon, but also on the backside of the Earth, it's bulging as well. Now, what's going on is because of the bulging that's happening and the rotation of the Earth, that is why we have the two tides there. So let's just talk about that. I guess I can do it. You know, I think I want to draw it in a little bit larger. I want to draw it a little bit larger. So I'll try to draw a larger Earth, not to scale, of course. And I'll just put the moon out here for reference, okay? And we already said that the bulging does not happen directly in the direction of the moon. It's actually off at some angle up here. I'm exaggerating it greatly, okay? Something like this. Looks like rings, but it's not really rings. All right, and we already said that the Earth is rotating in this direction, rotation. And we said this is like the North Pole. So you're like looking down at the Earth. So the Earth is rotating like this. Moon is also rotating like this. I guess I'll put this over here. And we have this bulging here. Now, it's important for you to note that the moon is orbiting the Earth, and the moon orbits every 27 days. I want to say that again because it's important. 27 days. The Earth rotates on its axis in 1 day. You know that. But the moon takes 27 times longer to go all the way around the planet. So I guess I want to draw another arrow that goes like this, orbit, right? And so in a given day, the bulge is going to more or less be like this. But over a few days, when the moon moves up here, the bulging is going to move over here. And a few more days later, the moon will be here, and the bulging will be like over here. So the bulging is changing positions, but over a one-day rotation of the Earth, it's pretty close to the same position because the moon doesn't move that far in one day. It does move in its orbit, but not that much in one Earth day because it takes 27 days for the moon to go around. I've got it tilted a little bit more extreme than I want. But anyway, you get the idea. If I'm over here, I'll put a little smiley face. Then what it means is any water that's underneath me is very shallow because it's being drawn over here and kind of stretched out in this direction. So this is low tide, right? Now, as the Earth rotates, remember it's rotating this direction, then I'm in a fixed position, but my position then goes over here. And over here, if I draw myself, if I can draw myself, right? Then see all the water that's in the ocean coastal areas right here, this is high tide. So I'll put high tide right here because the water will be deeper. And you can see the whole idea over here. If I get over here, I'll do this. Boy, it's hard to draw an upside down person, right? Then again, you get back to low tide because the water is very shallow there. And then if I can get over here, right? Something like this. This is again high tide. This is why we have 2 complete tide cycles every day. We have 2 high tides and we have 2 low tides. And the reason is because they're 2 bulges. Now I haven't explained why we have 2 bulges yet, so we have to wait for that. But once you understand that we do have 2 bulges, it makes total sense that as the Earth rotates around, then we're going to go through one high tide, then a low tide, then a high tide, then a low tide, and then we're going to go back to our starting position. Now, yes, over a period of days, the moon will move and the positions of these tides will shift, but still, in a given 24-hour period, we're still going to cut through all 4 of these positions. Now, as the Earth rotates, notice there's 24 hours in a day. That's rounding up. It's really 23 hours and like 56 minutes in a day. But you know that 6 times 4 is 24. There's 4 positions I've drawn. And so these tides, high to low and low to high, are spaced out every 6 hours. Because to go from here to here is 6 hours. And then to go from here to here is 6 hours. And then to go from here to here is 6 hours. And then go from here to here is 6 hours. Now I'm rounding here. It's not exactly 6 hours, and the reason because is we're assuming the moon to sort of be stationary here, but we know the moon travels through its orbit. So as the Earth rotates one time, the Earth has moved a little, and the positions of these bulges have moved a little bit. So it's really like 6 hours and like 12 minutes or something between the tides. A little bit longer because the position of the bulges have moved a little bit. But if you eliminate that in your mind, you can just say, well, it's about 6 hours there. So from a high tide to a low tide is about 6 hours. From a low tide to a high tide and so on is another 6 hours. So from one high tide to another high tide is 12 hours. So we generally say that the tides are 12 hours apart. That's what we mean. High tide to another high tide, that's about a 12-hour period. All right, make sure I said everything I want to say on this page. So now we know how the tides work. It's a gravitational interaction between the moon and the Earth. Bulges the oceans along an axis between the Earth-Moon line, but shifted slightly. We talked about how the bulge does move as the moon orbits the Earth. We talked about the Earth is rotating much faster than the moon's orbit, and so that's why we cut through these periods and we see the high tide and the low tides happen. But now we need to turn our attention to why do these bulges happen in the first place, because it is not at all obvious to anyone, I don't care who you are, that this backwards bulge on the other side makes any sense. It doesn't make intuitive sense. So we need to spend some time to talk about that. First, I'm going to draw the punchline. I'm going to draw the answer. And then you're going to be like, well, that doesn't make a lot of sense. And then I'm going to dive into it and dissect it to show you why the answer makes sense. But I have to start with the punchline. So if we draw this whole picture again, all right, with moon, and then we have Earth, I'll try to draw it a little bit bigger over here. Right? Now notice that we already said the bulge is kind of cocked at an angle to the moon because the rotation of the Earth is dragging the oceans around with it. But in this picture, I'm not going to draw any cocking because it's just going to make it cumbersome and difficult to draw. What I want to do is I want to draw sort of the force vectors acting on the ocean along the way. Remember, we said that the equation of gravity depends on the distance between the objects. The farther away the object is, the weaker the gravity, but it's not linear. It's not like you go twice as far away, separate them twice as much, and you have half the force. No, no, no. It's if you separate twice as far, you have 4 times less. Or divide by 4 is the force, right? Because of the squaring action. So as the force of gravity from the moon is affecting everything on the Earth, the distance between across the Earth is pretty great, and because it's an inverse square law, the force of gravity acting on the opposite sides of the planet is quite different. Now, a lot of books and teachers just say, well, you know, the moon is pulling the ocean here, and then the force is not as strong here, so it bulges out. But that's not really the whole story. The force of gravity from the Earth acting on the oceans is much, much stronger than the lunar gravity. So it's not just enough to say the moon's just pulling it. It's not like levitating it up. It's a much more nuanced answer. Let me draw some pictures, and then we will get there. All right, what we're going to do is I'm going to draw the force vectors acting on all of these things. Now, actually, it turns out that at the poles up here, the force vector acting on the ocean is actually acting inward, like this. And you might say, whoa, that doesn't make any sense. The moon is over here. Why is it pinching? Why is it acting, the force acting down? I have to draw a few pictures, so just kind of bear with me. And then over here, the force is a little longer, a little longer, a little longer, a little longer. Finally, it's the longest right here. And then you have the same kind of thing going on. A little longer, 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 like this. So you can imagine these force vectors acting on all the water, kind of squeezing it into a bulge. It's like take your skin with your thumbs and just push from the side, and it bulges up in the center. That's what's happening across the entire surface of the Earth here. Now, this sort of makes sense, but what doesn't make a lot of sense is going the other way. The force factors are actually doing something like this. A little bit longer, a little bit longer, a little bit longer, a little bit, whoop, that needs to be longer, a little bit longer, and then the same exact thing happens here. Here's longer, here's longer, here's longer, here's longer, and here's longer. So these are the force vectors acting on the water. Okay, the biggest ones are directly in the Earth-Moon line, and the other ones are acting at an angle. So these, if you accept this to be true, then these force vectors you can sort of see would squeeze the water out in both directions. But I've answered a question by giving you another question. Why are the force vectors like this? It doesn't seem to make sense. So what we have to do in order to dissect this, I told you tides are more complicated than they initially seemed. What we have to do in order to really understand this is we have to do a thought experiment. You know, Einstein was famous for doing thought experiments. We have to eliminate all the complexity. Let's not think of it as a solid sphere. Let's not think of it as a solid shell of water around the sphere. Let's just think of what this would look like in space with just a couple of objects. So remember this in your mind, and let's go over here and draw another system. Let's draw a moon system, but this will be a simpler system. And what we'll do here is some distance away from the moon, we'll have one object, not the Earth, just some rock or something. And there is another rock right here and another rock right here. So we put 3 pebbles in space, separated by equal distances here, and the whole thing is separated from the moon. And the way I set this up is that these rocks are at a distance away from the center, 1 Earth radius. So this is the Earth with the forces. We're simplifying it and saying, forget about, don't put any land anywhere, just put 1 pebble in the middle, 1 pebble at where the one edge of the Earth would be, and 1 pebble where the other edge of the Earth would be. All right, now the circle, the dotted line is not really here. We really just have these 3 pieces. What is going to happen? We said that gravity was an inverse square law. It gets weaker as we get farther away. So what's going to happen is that the nearest rock is going to have the biggest force, so that's a longer arrow. Then we have a pretty big force, medium-sized arrow. But this rock only has a small arrow acting on it because it's farther away by a great distance compared to this one. So if I have the moon and I have these 3 pebbles and I let them go and watch what would happen a few minutes in the future, a few days in the future, whatever. Well, what would happen would be that, let me draw the system again. We'll have the moon right here. What would happen is this one is being pulled more, and then this one's being pulled a little bit less, and then this one is being pulled a little bit less. So if I let it go, then what is actually going to happen is the center rock would be here. this rock would be much, much farther away, and then this rock would actually be much, much farther away right here. Because why? Because this rock is being pulled the most, this one's a little bit less, and this one is a little bit less. So if I can use my fingers are a little better. What's going to happen when I let it go, then what's going to happen is the whole system is going to be attracted to the moon, but this one's going to be attracted a little bit more, so it's going to move away. So these two are going to be kind of moving away like this, but this one's being attracted less than this one. So again, this one is going to be moving away from it. So as the system evolves, what's going to happen is this one will be in its new position, but these two will be both farther away. And if I draw my circle again, which represents sort of the diameter of the Earth, what happens? This one looks like it's farther away from the surface of the Earth, and this one looks like it's farther away from the surface of the Earth. So if I were only focusing my camera only on the center here, in other words, if I was riding around on the center pebble, if I was literally standing on the center pebble, looking over here at that pebble, and looking over there at that pebble, what would I see? To me, I don't even feel like I'm moving, but I see both of these pebbles moving away from me. So from my point of view, standing on the Earth, both pebbles are moving away from me. Both sides of the Earth are bulging away from me. Okay, so that is how generally things get stretched out as gravity acts on them. Okay, now we have to talk about, we're going to do another thought experiment, very, very, very similar to this one. This one is going to be very, very similar. I'm going to draw the moon again, and I'm going to draw 3 pebbles, but instead of lined up with the moon, we're going to draw 3 pebbles, one on top of the other, like this. And the moon is acting like this. Now the radius of the Earth, again, initially is where these pebbles are, like this. We just put 3 pebbles in space. So we're taking 2 situations, one when they're lined up in the direction of the moon, and one of them when they're perpendicular to the direction of the moon. So this would be like, this spot over here would be like a tiny part of ocean up here. So we've established that the ocean over here and here do tend to be stretched out. What's happening on the top and on the bottom? Well, what's going to happen is that the gravity is going to be acting in this direction here. On this guy over here, it's going to be acting in a similar strength like this. And then over here, a straight line distance, similar direction like this. So as time goes on, if I were to do this experiment with the 3 pebbles, they would all tend to be convergent. They would all be attracted to the moon. But what's going to happen in the next snapshot, let's draw a picture of it. If this is the moon, and I let this thing evolve, what's it going to look like? Well, the center pebble will be here, and it'll get closer, right? This pebble will have traveled down, so it will be maybe like this, and then this one will be like this. Again, the forces are something like this. But notice what's going on. If I look at my original dotted circle of the Earth, whoops, it's going to look something like this. So if I were riding along in the center rock, if I were standing on that center pebble, and there's a pebble above me and a pebble below me, and the moon is over there, I don't feel like I'm moving at all. From my point of view, that guy's just coming down towards me. And from below, I look, and this guy's coming up towards me, because that is what they have done. Yes, the whole system has moved this way, but these two have approached the center rock. So from the Earth point of view, top and bottom, it's like there's a force pushing them down. I'm going to say that again. From the Earth point of view, what makes it want to come in like this? A force pushing it down. In fact, if you know a little physics, this is a vector pointing this way. You can decompose it into a down force and a horizontal force. That down force is what's making them come together. So whenever I drew this punch line originally, I said, hey, these are the force vectors acting on the water. And I said, kind of doesn't make sense that this one's going up and down. The moon is over here. Well, the moon is attracting every bit in a diagonal line, and I can decompose that into a force this way and a force this way. And so what I'm drawing is the net result from the Earth point of view, of what that vector force will look like from the Earth point of view. When I'm riding along in this situation, if I'm riding along this pebble, from the Earth point of view, the pebbles have gotten farther from me, so it looks like everything's stretched out horizontally. If I'm riding along the Earth point of view in this direction, then top and bottom, the pebbles have gotten closer to me. So from my Earth-centric point of view, there's a force bulging these things outward, which I have drawn right here and right here. And from the Earth point of view here, there is a force pushing them in as they are coming closer to me, and I have drawn that up and down there. And if you go through and look at every point and do the same experiment with pebbles at everywhere, if you put pebbles in a circular kind of arc and just let them go, what's going to happen as they approach the moon, if I literally replace this circle with just pebbles in a circle and let the moon's gravity act on it, what's going to happen is the whole assembly is going to move toward the moon, but it's going to get stretched out and kind of spaghettified is what we call it. When you read about black holes, and one day I'll do a video on black holes, when you read about black holes, when an object enters a black hole, we call it spaghettification. You know, like a spaghetti noodle is very long and thin, because black hole's gravity is so powerful that it literally stretches it and rips it apart, really before it even gets into the black hole. Here is the same thing. It's just the gravity of the moon is not so great to destroy us. It's just stretching things out a little bit. And because water takes the shape of its container and forces can be transmitted through water, then we have the two bulges on both sides of the planet. Now, the next thing I'm going to say is probably one of the most important things in this whole lesson, so I want you to listen carefully to this. I've drawn a bunch of little tiny vector arrows, and you can think of every molecule of water having a different arrow associated with it here. The reason the tides do their thing for the oceans and not really for lakes is because for this effect to be noticeable, you need a very large body of water. Because what happens is this force is pushing a couple of molecules, and there's another force on the adjacent molecules, but when this one gets pushed, it's pushing the adjacent molecules. When this one gets pushed, it's pushing the adjacent molecules. When this one is pushed, it's pushing the adjacent molecules. So the reason we get a very large bulge on one side, big enough to notice, is because of the aggregate pushing of all of these things throughout the fluid that we call water over thousands of miles. Water is an incompressible fluid. It doesn't compress. When you push on it, it transmits the force through the liquid. Same with a solid. They're mostly incompressible. You can compress some solids, depends on the solid. But water is almost completely incompressible. So when these forces are very, very tiny coming from the moon, right? But especially compared to the gravity of the Earth, which is much closer. But acting over thousands of miles, they can add up. It's like if I have a tray or a bathtub of water, and I take a hairdryer and I blow the water with the dryer, or maybe I have 10 dryers and I blow 10 hair dryers blowing on the water. One little hairdryer is not going to do much of a force to change what's happening on the surface of the water. But if I have 10 or 20 of them blowing, the aggregate of adding them all up over a large surface area of the bathtub can maybe push the water to make it a little higher on one side. And that's what's happening here. These arrows I've exaggerated. They're very, very small, but acting over thousands of miles, they add up because the fluid transmits the forces from one molecule to the next, and then so you can see the effect of one bulge here and one bulge there. And that's why lakes and rivers and streams don't have a noticeable tide. Now, very, very large lakes you can actually measure, but most little ponds, you don't see the tide go up and the tide go down because the gravitational force from the moon is much weaker than the Earth. So it's just going to be dominated by Earth's gravity, and you're just not going to notice it. You need thousands of miles of these forces adding up for us to see the effect. So that is an introduction to how tides work. I told you it was more complicated than initially it might seem, and the other part of it is I've completely ignored other effects. For instance, these bulges are happening because of the moon, but the sun is much, much more massive than the Earth and the moon. It's farther away, but it's much more massive, and the sun actually attracts the oceans also. So sometimes when the Earth and the moon and the sun are all lined up, the tide is even bigger. Like here we have this and we have the moon. What if the sun is actually over there, like where my lights are? Then everything's lined up and these tides are going to be even bigger. But what if the moon's over here and the sun's over here? Then you're going to have a combination of effects from the moon and the sun. And so the sun has an effect on the height of the tide as well. But we don't want to introduce too many variables because it becomes impossible to understand. So what I'd like you to do is watch this again till you feel like you understand the tides. And in a future video, we're going to take this a step further. We're going to talk about how the tides impact other things. For instance, the fact that the face of the moon is always the same face that we see from Earth. That is indirectly due to the tides. The fact that the moon actually is going away from us in its orbit and getting farther from us over time, that is partially due to the tides. We have a lot more to cover here. This is just how the tides work, but I'll do other lessons in the future where we take these effects and see how they affect other aspects of our everyday life.